So like I said, we're just gonna kind of go through the homework, and then if anybody has a general question or whatever, feel free to stop me. Just gonna take his mask off because so if you want to follow along, right now up on my screen, I just have the homework 5 instructions. And then these are just the answers. That way I can just walk through it. So yeah, let's get started. So 5A and 5B both are referring to Wisconsin phosphate levels in drinking water reservoirs. And it says the level should be less than or equal to 25 parts per billion to be considered safe. Phosphate measurements with the following characteristics are made. So there's 5A, A and B, then 5B, A and B, and they all have different levels. And then it says for each set of measurements, perform a hypothesis test to determine whether the phosphate level is safe within the safe range with a 95% confidence. Okay, so this has sample of 25, sample mean of 24 parts per billion, sample standard deviation of 2.5 parts per billion, and then an alpha of 0.05 because we want 95% confidence. We've said this multiple times. This alpha level of 0.05 is almost always going to be the level unless it's otherwise stated. That's pretty much standard throughout science, I guess you could say. So our null hypothesis in this case is that the water is greater than 25 parts per billion, which just means it's unsafe to drink. Okay, so that means our alternative is that it's, which would be safe. Okay, so you need to find, I don't know what the hell that is. So we don't want a basketball court. So our T statistic is the mu naught minus the X bar over your sample standard deviation over the square root of the sample size. And so this 25 is coming from the question where it says the water must be less than or equal to 25 parts per billion to be considered safe. Okay, so that's where that 25 is coming from. And so to find our T statistic, we would just do 25 minus our X bar of 24, which is this specific sample's mean, then 2.5 over the square root of our N, which is 5. Okay, and so when you work this out, this is 1 up top divided by, I did 5 because that's what the square root of 25 is. So 2.5 divided by 5 is 0.5, right? So it's 1 divided by 0.5 is 2. I think that's the math just checks out. But anyway, so our T statistic for 5AA is 2. And then all we have to do next is find our T critical value, which would be in the back of the book. So we're looking at a one tail, alpha 0.05, and a degrees of freedom. In this case, degrees of freedom is equal to the sample size minus 1. Recall further along, the degrees of freedom means, or like it's different. So in this case, it's n minus 1. So then when you look this up in the back of the book, I think it's on page 494 or something like that, or that might be the Z table. but you get a value of 1.711. So in this sense, our T stat is greater than our T critical. And so we therefore reject the null. And so that means the water is safe. Okay. So it's critical that you remember that when you're comparing T statistics, you compare them to T critical values. When you're doing P values, you're comparing them to the alpha level of 0.05. So further on we got into the class, I was noticing some people were doing a T stat versus a P value, the 0.05, and therefore like you might get the same outcome, but in certain cases you might not. So that could lead you to be wrong in the answer. So I'm just gonna put this up in this top corner here. When the T stat is greater than T crit, reject. When T stat is less than T crit, fail to reject. Okay, and then when P is less than 0.05, reject. When P is greater than 0.05, fail to reject. I don't know if we're gonna get to like the chi-stat, chi-squared stuff today, but when we do, I'll put up what we need for that one. And then I highly recommend the day of the exam to just write this up at the top of your paper. It's something that still trips me up today. In my head, literally when I was writing that, I had to remind myself that that was correct. So, so yeah, that's 5A. Anybody have a question on that one?
How do you know like whether to do a one-tail or a two-tail hypothesis now?
Great question. So it just is based on the amount of samples you have.
Oh, okay.
So like if we were doing like 2 different areas of water
Okay.
and comparing it at like this 25, then we'd use a two-tail.
Okay, got it.
All right. So I'm gonna erase some of this stuff because it's basically the same question. We just have a different X bar. So B is now our X bar is 26 parts per billion, and that's the same. That's the same. These are the same. And so in this case, the only thing that changes is this value. The outcome here, that's going to remain the same. And so right now I got to do just -1, and then this is the same 0.5, so it's -2. And so here our T stat is now less than T critical. And so I know a lot of people, especially Mike's been saying, like, look at the absolute value and that kind of stuff. Another way to think of it is like if you're comparing a negative T statistic, pretend the critical value is negative, and then look at it like this. So let's say this is 0, right? And so if this is our T critical of -1.711, and this is our negative T stat, it's less than that. Does that kind of make sense? So we would then fail to reject this one. But in the other one, it was 1.711. It's 2. And this is greater than that. Like you're basically, like it's like which one's closer to 0? I don't know if that makes sense. But so that's why in this sense we would fail to reject this null hypothesis.
Does that mean the water's unsafe?
Oh, yeah, sorry. I didn't change that. Hold on. So that's 5AB. Is there any questions going on? No? So moving right along then. 5B is the same idea of the question. We just have a different sample size. Sorry, 5. Yeah, because 5A, part A was the same as part 5B, part A. That's what he wrote here. So 5B, part A is, yeah, the exact same thing. So I don't really know why we did it twice, but okay. So we're doing 5B, part B. So our sample size is.
So wait, for 5B, there's no part A?
No, there is. It's just the exact same parameters as 5A, part A. Sample is the same, that's the same. And then, yeah, these are the same. So then in this sense, we change this value and we change the n value to 16. I'm not going to try to do the math in my head this time, but so 25 minus 24, and then the square root of 16 here on the bottom. So then when you work this out, you get 1.6. And then this, instead of being 24, is now going to be 15. And so that changes this value to 1.753. And so in this sense, our T stat is less than our T critical. So we would fail to reject the null. So we would say that the water is unsafe. And this was basically just showing you that compared to 5A, part A, where we had the same average parts per billion, but a higher sample size, it changes the outcome of what we decide. So, yeah. Any questions on that? Yep, that's fine. So remember, especially like moving forward, I don't think Mike's going to be a stickler. I know that I was pretty slack about it on the homework. I usually just wrote it at the top. But make sure that you give some sort of statement sentence after your outcome, just to like reiterate what the outcome is, especially moving forward when you're doing analyses. So
Wait, when in the hypothesis, is it still out of 25 or would it be 24?
it's at 25
Wow.
based on the question. So because that was like the base level it gave in the question, was that if the water was below or was above this 25 threshold,
Right.
then it would be unsafe to drink.
Is the U, that's like what is like the U0, the mean, like 25, like is that just from the question?
Mhm.
Okay.
Yeah. So like that's I know that we talked about this the other day. That's what we were testing. It's just if it's going to be safe or unsafe.
Yeah.
So since it gave us like a said if the water is above 25, then it's unsafe to drink.
Yeah.
So then that became our no.
Yeah. Okay.
All right. Moving right along here.
personal things in there.
So 5.6 had to do with something, World War II. I don't know. Does anybody have the question in front of them?
Yeah.
Yeah. Somebody want to kind of give me a gist of it? Something about World War II? I just know about it.
The effects of nutritional changes on human.
5.6.
Yeah. Prior to World War II, indicated the heights of adult Japanese males.
Okay, so it's height of people pre and post World War II, something like that. Okay. So pre World War II, you had a mean. Remember, the mu is symbolized of a population, whereas X bar symbolizes a sample. You can also think of it as the Greek letters symbolizes populations, whereas regular run-of-the-mill alphabet letters signifies a sample. So we had a average height of 64 inches and a standard deviation of 2 inches. And then our sample, we had 25 individuals and we had a sample mean of 66.5. And then a standard deviation of 3. Okay. So part A was getting a confidence interval, right? Okay. So what we want to do is we want to find first our T stat. So again, that's mu minus X bar over the standard deviation over the square root of n. And so we don't, so we want to find a 95% confidence interval for the population mean. Is that correct? I think that's what we're going for.
Yeah.
And so in this sense, you leave mu the same, or you just leave it as mu, and then you put your sample standard sample mean in, and then sample standard deviation over the sample size of 25. And so you can think of this as, you know, your mu is in the middle of this confidence interval here. And so we want to find the T critical to finish through this problem. So the T critical is alpha of 0.05 and degrees of freedom of 24. And we get 2.064 when you find this in the back of the book. And then, so it'd be negative 2.064 and then 2.064. And then it's, you just do algebra to find either side of this. So, holy hell, 5, yeah, I can't do this out. I can't do this in my head. But when you find this bottom, you multiply it to get it out, and then you add 66.5 to either side to then leave mu by itself. And so when you work through that,
Where did the critical value come from?
the back of the book, the T table with an alpha of 0.5 and the degrees of freedom of 24.
No, Kale.
Okay, so 3 divided by 5 is equal to 0.6. So then if you multiply 2.064 times 0.6, you get 1.66.5. you get 1.238. Wow, that's really close. 2.2384. And then if you add 66.5 to it, you get the upper bound. So then if you do 0.6 times the negative of the same, you should get the same value. Yeah, so then you get negative 1.23384. And then you add 66.5 to both sides, and then you're left with mu in the center, and you have 67.74 and 65.26. So your statement here would say something along the lines of, we're 95% confident that the pre-World War II height was somewhere between 65.26 inches and 67.74 inches.
So you took the T-stat and set it equal to 2.064 and negative 2.064, and then solved for you both times.
Sorry, say it again.
You took the T-stat stuff and set it equal to 2.064 and negative 2.064 to
Yeah.
solve for mu each time.
Yeah,
Okay,
yeah.
thank you.
And so, okay, yeah, that's part of it. He's just doing the confidence interval. Okay. Yeah. So then, I'm gonna just write this part up here for A. So A, 65.26 is less than or equal to mu, which is less than or equal to 67.74. And so part B was doing the chi-squared confidence interval. Should really have this question up.
Population variance.
The population variance.
Hey, Jacob,
Yes.
how did you get from the 2.064 to the 1.25? And you're trying to do the math on the calculator.
The 2 point,
So like the 2.064 to like the 1.234. How did you?
you multiply that by 0.6, and the 0.6 comes from the 3 divided by, yes.
Okay.
Yeah. Determine the critical values. Why does it say that? Is this the right? Oh, that's not even the question.
152.
Thank you. I'm like looking at something completely different. Okay. Sorry. Try to get this out of your way. Okay. So B, calculate the 95% confidence interval for the population variance. So it's roughly the same idea, where we're gonna have a chi-squared critical value. And for this, you use the same degrees of freedom of 24 and an alpha of 0.05. And then when you look at the chi table in the back of the book, you get a value. So the chi-squared table in the back of the book is a little bit differently, because you have to look at both bounds. So you have to look at the lower bound and the upper bound. So we have a degree of freedom of, what is that? 24. So you go down to the left side of the column, and then the lower bound is the 0.025, because you're trying to find 5% in total. So you want to look at 2.5% and 2.5% on the other side of the distribution. And so the 2.025 column at 24 is 12.4. And the 0.975 column at the same confidence or degrees of freedom is 39.4. Are you guys seeing that in the table? All right. And so but anyway, so that's where these numbers I'm about to write are coming from, is the chi-squared in the back of the book. So you get, I'm gonna put lower 12.4, and then upper is, what did I say, 39.4? Yeah. All right. And so then we have your chi-squared, and we're gonna try to solve for it. And it's n-1 times sample standard deviation divided by the sample or the population standard deviation. Okay, and so it would be 24 times 9, because we have 3 squared is 9, over the square root or the whatever population variance. And then we have those equal to 12.4. This is our confidence interval here. All right. And then when you work this out, 24 times 9 is 24 times 9, 216. And then we divide 216 by either of these bounds to find the center. So 216 divided by 39.3.4, and then 216 divided by 12.4, and you should get 5.49 and 17.42 or something right around there. And so we're going to switch the way that the signs are facing, just to make sense. And that has to do with dividing fractions or multiplying fractions, or one of the two of those things. Something that we didn't do in this class, but it's a mathematical function. So that would then be your population variance 95% confidence interval. And if you wanted to find the population standard deviation, you would just square root the whole thing. You'd get rid of that. You would square both of those sides there.
Do you think that will be on the, like, the exam? Because that was on the last exam. Wasn't this on the midterm? This was on the midterm.
Chapter 5 of the midterm?
No, but confidence intervals were.
Oh.
This was like what we did in the, that's why I was confused. It was on this homework, but.
Oh, maybe. I have no idea. He doesn't tell me what's going to be on. I think he knows that I talk to you guys too much.
Is that from the midterm and before going to be on the final, or is it just after the midterm?
It's going to be stuff after the midterm, but like basic statistical knowledge is going to be cumulative throughout the whole thing. So, like I was saying, I don't know if you're here yet, but like stuff like probability, I doubt will be on there. But like we were using stuff in the last chapter with like Poisson distributions, and so like that kind of knowledge is going to be kind of through the whole thing. But I doubt he's going to say like, what's the probability of this? Because like we already tested you on that.
Jacob, why isn't the theta, why wouldn't it be 2 squared down below? Isn't the population 2 inches? Why wouldn't it be 2 squared underneath the 24 times 9? You see what I mean?
2
Like,
right here.
yeah, because like, isn't the population,
What?
2?
Yeah, but this is just doing the variance. So the variance just means the standard deviation squared or vice versa. So like if you said population standard deviation, then we would square root the bottom here. And you take the square root, you get rid of that squares of the standard deviation. Right? All right. So
Can you get those? No.
5.49,
5.
17.42.
Well, that was part A.
How do we see?
There you go, right, that's part B of it.
And then C is doing page 157.
Code to that.
C has the mean height changed since World War II. Write out a hypothesis associated with this question. So in that sense, we're just gonna do a hypothesis test. So the null is that the population mean is equal to the population of pre-World War II, aka 64 inches. The alternative is that it is not equal to it. And so then we would do our t-stat. And he has it 64 minus 66.5 over 3 over the square root of 25. And when you work that out, you get, see now he has this absolute value of this whole thing. You get 4.17. So when you look at the T critical value of what we looked at earlier, which is that 2.064. The first one's a 0. The t-stat is then greater than your t-crit, which leads you to reject the null, saying that the average height is not equal to the average height before World War II. Okay.
Like, so when would we like absolute value, they're gonna like do the other way of?
I would just say do the absolute value the whole time. I'm just like, I was confused when we were going over this in class, and he like does it one time but doesn't do it the other time. I would say to be safe, just do it all the time. That last one was kind of weird because like I know when I wrote out too, it's just like doesn't really make sense. But I would just say do the absolute value of it. Okay, so that is part C. So use that. Great. And then D is doing the variance of height, has a variance of heights associated changed since World War II. Again, write out the hypothesis. All right, so null is now that the variance is this, or we're just gonna roll with the standard deviation. That way we don't have to square anything. Of the variance or the standard deviation is the same as the standard deviation of the pre, which is 2 inches. So dang, Mike, you can write anything out for me. chi-squared. Yeah, it's got it. So I'm gonna find chi-squared set, which is n minus 1, 2. So we have 24 times 9 over 4. That is equal to 24, 54. This doesn't make sense in my head. The way he did it on this homework, he just has a distribution. Like, put this on the back burner here. This is what he wrote out. 3, which is our sample. And then the bounds of that confidence interval, if you took the square root of the whole thing, which then became 2.34 and 4.17. So you put 4.17 over here, and you put 2.34 here. And then he said since our that is here, because we have a 2, he said you reject the null. This does not equal this. Ta-da. Which I guess makes sense because this is our 95% confidence interval. But like you guys, I also haven't done chapter 5 since we did chapter 5, so it's a little lost in my head as well. So
Wait, where is the 2.34? Oh, is that the flip?
yeah, that's like if you took the square root of these two, you get 2.34 and 4.17. So I was saying that like I was starting to do it where I was going to solve for a chi-squared stat and a critical value, but then I was looking at the paper and that's the way he solved it, or his way he did it was he just said that because the value we found or the pre-value was outside that confidence interval that we're going to reject it.
Gotcha.
Yeah, because you reject with 95% confidence. All right, let's move on because that was sucks. E, relate the confidence intervals in A and B to the hypothesis in C and D. So it says that the pre-average lies outside of the 95% confidence for the average, and that the pre-standard deviation lies outside the confidence interval for the standard deviation. So in both cases, reject the null. So like we just showed here, and then the average 64 is also outside of this confidence interval here, to be done this way. All right. I wouldn't worry too much about this one. Seems like a lot. Any questions? Moving on. Please say no. Yeah, moving forward. All right. So then, oh, okay, cool. We didn't do that one. 5.12, better, more information to specify value. What was this question? In test hypothesis, the decision to accept or reject the null can be made by comparing the test statistic to an appropriate critical value. Alternatively, one can determine
the p-value of the test and compare that value to the chosen level. Discuss the advantage of the second method over the critical value.
Oh, so he's just saying like, is it better to compare a p-value to the alpha or a t-statistic to a t-critical value? And it's just better because you have more information to specify the value of t. Than to use the t-stat value. So I guess when you can do both, compare the p-value.
All right, moving on to chapter 6, because chapter 5 is annoying. Oops. Chapter 6, 3. Okay, so in a healthy adult male, sciatic nerve values are normally distributed with an average of 65 and a standard deviation of 5. There's 16 subjects, yada, yada, yada. And the 16 subjects had a mean of 55. Do the data provide sufficient evidence to indicate the conduction velocities are significantly lower than the poisoned individuals? Okay, so we have our population values up here, and then our sample 16, and the average, and the standard deviation. So our degrees of freedom are 15. So our null is that the average is greater than 65, and our alternative is that the average is less than 65. Specifies that this is a one-tail. And so we're just gonna do the t-stat just like we've been doing it. So minus x bar over s over square root n equals 65 minus 55 over 7 over square root of 16 is just 4. And then you get 5.71, and then a t-crit with alpha 0.05 and the degrees of freedom of 15, you get 1.753. So our t-stat is greater than the t-crit. And so we then reject the null. So we would say that they are significantly slower than in the poisoned individuals, because we're rejecting the null that they're greater than that.
I think you just had to do A for that one.
Yeah.
I'm gonna just kind of start skipping forward. 6.4 was another confidence interval. 6.6, it's another one like that. You're just having a t-stat and a t-critical value. 6.5 is the Wilcoxon sign rank test. We'll do that one since that's something we haven't done yet today. So moving along.
Yeah, no.
Okay, so this one is fasting blood glucose level of 9 women, oral contraceptives for 6 months. Thought that the mean fasting blood glucose level in women not using contraceptives is 3.8 millimoles per liter. Test whether there's evidence that the use of contraceptive raises glucose levels. So 6.15, 6.15. So
I think
I think it's just this one.
Oh,
Just pulling up the notes right now. So this is a non-parametric test, which means that there's no assumption of the distribution. That is like a normal distribution. So we're going to be using the median instead of the mean. Yeah, so like a non-parametric is just you don't assume anything about the underlying distribution. So basically saying like we're not going to assume it's a normal distribution. So let's see here. Read the question again. Okay. So I'm gonna just write the this column thing here. So these are the levels of glucose level for the women.
Wait, is this your, what is this? Your-
It doesn't matter. It's not what you do.
Yeah. And then this is our A column. Then we're comparing it to that 3.8 level. And then we're going to do the A column minus the B column. And then we're going to rank them. So when you do A minus B for all of these, this is the column that you get, okay?
How do you know when to use this or another test?
This is just a, it should specify
Okay.
that it's going to be a non-parametric test. I think in the homework question, or in the homework, he might have said, yeah, so in the homework assignment, he said 6:15, do this problem using using the sign rank test. So like, even though it doesn't say it in the question in the book that it's a non-parametric, he wanted you guys to do this one as a non-parametric. So he'll make it known, whether it's saying like some questions say like, don't assume normality, or like not assuming normality of the data, something along those lines. Or he might just flat out say like, use this test. Actually, on the exam, you probably won't say it like that, but
Does it matter if you do B minus A or A minus B, as long as like?
yeah, so think of it as like, you always want to do like your observed data minus like, because all these numbers are gonna be the same. So like the observed minus the same numbers. I don't want to call this the expected, but like it's the expected average of the data set.
Mm-hmm.
And so we're just comparing these individuals to that average. And so the idea with the Wilcox and sign rank test is you rank them lowest to highest, and you're just specifying if it's negative or not, but you keep it like low to high. So plus minus rank. So the first lowest one is this 0.12. So that would be 1. Then the next one is 0.19. And then I'm just going to put a negative next to it. So you don't rank them separately, you rank them together, and you just specify how many negative ones you have. All right. So then it's 0.25. All right. Now I'm just going to go down the list because I already have the list here.
So there's a lot of.
Okay. And so our null, and remember we're using this theta because it's the median. So theta means median, or non-parametric. So what are we testing again? Test whether there's evidence that the use of contraceptives raises glucose levels, assume symmetry. So like this question even specifies that it should be a regular one. So our null is that it, I literally just forgot what we're doing. Raises glucose levels. So we're saying that it doesn't raise it, and that the alternative is that it does raise. Right, okay. And so you want to sum up your negative values and sum up the positive values. All right, so sum of negative ranks equals 5, because you have 3 and 2, those are your negative ones, so 2 plus 3 is 5. And sum of the positive ranks is 40. Yeah, it's 40. All right, so then when you look at your W stat, you're looking for the minimum value between these two sums. Okay, and then P n of 9, one tail, W less than W stat equals 0.0195. So your p-value is less than your alpha, which we then reject the null. That's where I'm about to double check that here. I believe it's in the Wilcoxon table. So we have a W stat of 5 and an N of 9. W stat of 5, N of 9.
Okay.
All right, so you just go your W stat down the left side of the table, and then whatever your N value over the top, and then find where they connect, and that gives you your W. That gives you your p-value, and then you compare your p-value to 0.05 or your alpha. So we're rejecting the null, saying that this contraceptive raises glucose levels. All right, everyone following that one?
What table was that? I just want to write it down.
The Wilcoxon table. I'm not sure what page it's on.
These are all in like the class documents, right? Are these are all the course documents.
Yeah, he should have all these tables in the course documents. Some of the ones on like the PDFs he gave have like more precise numbers, or they might like I think like for example the chi distribution in his thing online, it might go past 80 degrees of freedom. So like I don't know. It's good to have them handy. Maybe print them out. I don't know. Whatever you want to do. There's some that like I remember there's some that like it's better to look in the book, and others that it's better to look at the one he has, because like the degrees of freedom either are more specified, or like I think there's one where like it ends at 30 degrees of freedom, then it goes 30, 40, 50, 60, etc. But the one online goes 31, 32, 33, 34, etc. And it goes like up to 50 by counting by one. And in that sense, it's easier, or like it's better, because like if you have one that's 35 and you look at the book and it's just 30 to 40, you gotta take a guess. And then he wanted us to do it binomially. Maybe you were right. We did do it twice.
Yeah, that's what it went twice. I'm not sure why.
Yeah, and then the next one we do is the binomial test. The same problem. Oh, this is going back to probabilities. So this one you're just this problem. Okay, as the most costume ties were discarded.
Just thought this is the only statistics class
I'm trying to figure out where we're getting these values from, but all right. So these are the same. I should have. Those aren't. Those are the same, and then P plus equals P minus, because you have the same probability of being either over or below. So instead of ranking them, you're just saying if they're positive or negative. So like positive, negative, positive, positive, negative, positive. And then we're saying that the probability of it being basically above 3.8 and being below 3.8 is even. So probability of negative, probability of positive or negative is 1/2. Right? So looking for null is correct. So the probability of 2 or fewer among 9 is the question he asked you. And so saying 2 or fewer is the same as saying what is the probability of nobody, the probability of 1 person, or the probability of 2 people being positive. Yeah. And so we write this out in a binomial fashion. Oh man, now I gotta get off the binomial. 0. N over K times the probability of K, probability of N. So, or this is like Q and P or something like that. So basically, since we have 1/2 on both of these, they're both 1/2. But let's say like the probability of it being positive or whatever is like 0.4, then this one would be 0.4, this one would be 0.6. So it's like the probability of it happening, the probability of it not happening. And so this is then equal to 1, which is this value. 1/2 to the 0 is also 1. And then 1/2 to the 9 is 1 over 5/12. Okay. And then okay, so then the probability of 1 on 1, 1/2, 1, 1/2, 8, and then P2, 9, 2, 1/2, 2, 1/2, 7. And so when you do the binomial, what was that? Pascal's triangle? Is that what it was called?
Yeah.
You guys remember that? So that's how you get this for these first numbers. So this would be 9 times 1/2, and then 1/2 times. So basically, it's this value again at the end, because these two and these two are always going to equal 1/2 to the 9. So this one's kind of an easy one. And then this is equal to 36, and then 5/12.
Wait, can you explain the Pascal's triangle? How do you get the numbers from it?
Yeah, so it's the Pascal's triangle is easier if you're doing like probably up to the 5. But it's like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And it's basically saying, like, let's say we were working on this one. If you had 0, 1, 2, 3, 4, if you were working out from 4, right? And you did 1, that value is equal to this one here. And if you said 4, 2, that would be equal to this. And that's after you do, shoot, does anybody remember that formula off the top of the head for the binomial? It's like, that's great. Great. What chapter it was? 3. Okay, here it is.
Would that be the factor or the fifth row?
So recall that this is n k is equal to n factorial. Oh, can you read that formula that's written there? N factorial
Oh,
over
this is like
N minus k factorial, k factorial.
times k factorial.
Well, the factorial is on the outside of the parenthesis for that one, yeah.
Times k factorial.
Yeah.
So, so the Pascal's triangle is just basically a quick way to avoid doing that junk
Yeah.
here. So it's saying like 9 factorial divided by 9 minus 2 factorial
Okay.
times 2 factorial would give you 36. All right.
Jacob,
Yes.
how do you get that half?
We were just saying that the probability, I think it's part of the question. No, it's not, of course not. Yeah, we're doing the sign test for the same one. We were just saying that we're just assuming that the probability of you being above the glucose level and below the glucose level is just the same. And we're just running off that assumption. Yeah. Yeah, and we're just running off that assumption. And then, so then the probability of 2 or fewer among 9 is then, once you add all of those up, is 46 over 512. Okay, and then is 9, whatever. Nah. And then that is equal to 0.090. And so since 0.090 is a p-value, we compare that to an alpha value, it's greater than, so you would fail to reject the this may be greater than 3.8. That's your answer in the sign test.
Jacob, can you explain real quickly why you got rid of the, like, why is it 9 times 1 over 512? Like, is it because the 1/2 raised to 1, like there's such a minute value? So you get
No, it's just like, because when you work this out, this value, if you're looking at a binomial and the 0, it's always going to be 1. This one's always going to be 1.
right.
Anything raised to the 0 power is 1.
Mhm.
And then 1/2 to the 9 is equal to 1 over 512.
Right.
And so the reason that I just wrote 1 over 512 for both of these is because these multiplied against each other, no matter how many, like, no matter if it's 1/2 to the 3rd plus or times 1/2 to the 6th, it's always going to be 1/2 to the 9 technically.
Oh, okay.
And so, like, that's what I was saying, like, it's you would get a more complex answer if, like, let's say the probability of being positive was 0.6 and the probability of being negative was 0.4, then it would be like 0.6, 0.4, 0.6 to the 1, 0.4 to the 8, 0.6 to the, et cetera. So I just it's always gonna be the 1/512, just because 1/2 to the 9 is 1/512.
Why are we doing the probability of 2 or fewer?
I don't know. I thought that was the question. I think that was the question. I don't- Yeah, I don't know. I think it said it somewhere in the instructions.
Okay,
It said to do it the binomial distribution as well for that one. All right, so now we're gonna move on to 7. Let me get the chapter 7.
Zach, you want to bring me the,
Behind my backpack. Yeah.
Which one's are you going through today?
I'm gonna try to get through 7 and 8, but depending on the time, we might have to stop at 7. What's the left? Yeah, same time. That one, since it's Friday, might go a little longer. Maybe not. Okay, so this is using 2 sample t-tests.
7.1.
Yeah.
We went over chapter 7 in process, can we skip to chapter 8?
Oh, did we go over chapter 7?
You spent like a whole process.
Awesome, awesome. That makes it even easier. Oh, that's what, did we do that on, like, not
The day before you
The
presented.
day before you
Oh,
presented.
jeez. Alright. Good call on that.
I just knew it was gonna take a long time, because it was like a lot.
Oh, the whole chapter 7, perfect.
No, but this is a note on it.
Yeah,
Just like 7, like how to know like to use what test when. Cause that's what I get confused about.
in the sense of like,
Like it's.
paired sample and paired
Yeah,
sample Wilcoxon. Okay, so I'm just gonna stare at the notes while I discuss this though, so. Paired sample t-test, paired sample Wilcoxon sign ring test, and paired sample binomial test. They're all when you're comparing, like the same sample, just like 2 different things, so like before and afters.
And which one is that for?
Any of the ones that say paired sample, so like the t-test is when you assume normality of the data. It's a parametric test, and then there's 2 different non-parametric tests, the paired sample Wilcoxon and the paired sample binomial. And so like, trying to give an example here. So like the paired sample Wilcoxon would just be like, if you're looking at the whole group and you're trying to figure out if it would fail to reject or reject the null. Whereas the paired sample binomial is where you're choosing a probability of certain things to happen within that sample. So like, for example, like the ones in his notes, it's just like, is the medication effective or not? And you would use the Wilcoxon sign ring test for that. And then the paired sample binomial is saying 1 or fewer among 10 trials. Like the probability of that happening, the probability of the medication to be effective for 1 or fewer.
That's fine, no.
Yeah.
Okay, that makes sense.
So think of binomial as like looking at the probability of like a specific event happening, whereas the paired sample Wilcoxon sign rank test is like looking at everything, or like looking at the whole thing.
And then how about like there was 2 sample t-tests and
Mhm.
stuff like that.
So the 2 sample
For the
t-test.
paired sample, like, yeah.
Yeah, so the 2 sample t-test is used when you have 2 samples, like 2 rivers, or like a group of, you know, women under this age and a group of women over this age, and you're comparing it to some overlying, or I guess underlying, like assumption.
Okay, so this is where I get confused because the 2 sample is like, you're comparing like 2 different things. That makes sense. But then for the first one, he did a 2 sample with a before and after of like the question that asked for like the befores or something and the afters or something. It's not like 2 different things.
In the notes
No, for like the first homework problem.
on 7.
Yeah.
What number was it?
Number 1. That's why I already like I got confused because it says use a different test for samples that were before and after. But then for the first one, they used their 2 samples.
Sure.
So,
There are 2 samples.
yeah, because it says to use a paired sample t-test based on before and after differences. Or is a 1 sample t-test based on before and after differences? So why do we use a 2 sample for before and after differences?
You should have used just a 2 sample test for 7 and 1, before and after. And so I think he was just trying to give you an introduction to 2 sample tests, or maybe.
Yeah, but like, how do you like know to use the 2 sample? Because if I like read the notes and it said paired sample t-test is a 1 sample t-test based on before and after differences, I would do a paired sample t. Like I wouldn't do a 2 sample t-test because it says to do something else.
No,
That's why I'm confused. Yeah.
Trying to figure out 7-1, make an approximation. That's all he says. Paired sample t-test, paired sample Wilcoxon. Complicated, sometimes better. Okay, I think it's on page 4 on his notes.
Yeah, okay. 2 sample.
Yeah, because it says, I have that first where he says complicated. I have that, like I made a mark that said book method. And then the other one is this Welch's approximate test. And it's a simpler procedure. Independent samples, populations of normal distribution, population variances may be unequal. You will only use the simpler procedure. I'm not sure, Gianna. I would email him that question.
Okay, so like broadly speaking, you use a paired sample with Coxon when you're looking at the whole data set.
You
Yeah, I
use,
just like want to know
yeah.
when I should use each test.
Yeah.
Because I know how to do them, but like I don't know when to use each one.
Okay, so in the way I think of it is that a paired sample, you're looking at the same group before and after something happens.
Okay.
Okay, whether it's you took a medication, whether it's there was a new law enacted, whether it's, you know, now there's fishing in that area, whatever it is. Okay, and then a 2 sample is you're looking at 2
individual samples that are not the same thing. So two separate rivers, one with pollution, one without. Two separate groups of women, one this age range, one this age range, with the same medication involved.
Okay.
And then parametric and non-parametric are just based on assumption of the underlying distribution. So if you're going to assume that the underlying distribution is normal, then you would use a parametric test. And if you would assume that it's not normal, then you would use a non-parametric test.
The underlying what?
Distribution.
Okay.
So like, trying to think. So let's say, I don't know. You have two groups of women and you have like 30 and under and above 30, and there's some sort of medication, and it's like, what are the effects of the medication, like increased levels of probability to have a heart attack or something like that. Like you would assume, just based on what we know about health in humans, that the older you are, probably the more likely you are to have a heart attack in general. So like in that sense, you might want to use a non-parametric test, because you shouldn't assume that that is normal, that like the older you get, you're going to be kind of skewed towards a higher probability of having a heart attack anyway,
Okay.
just because you're
I
older.
remember when we did we did these and the homework, it said like it told you.
Yeah, yeah, that's what, like, I would assume his questions in the test are going to be kind of the same thing, where it's like, you know, assuming normality of the data, or like assuming the data is not normal, yada, 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 yada. So I don't think he's going to say like flat out use a parametric, use a non-parametric, but he's going to give you something to where you should be able to infer what test you want to use.
So in the pair sample, that's when you use like the after minus before, or vice versa.
Yeah. Yeah. All right. So we're all good then. We're going to move on to chapter 8. Yeah. One-way ANOVAs, analysis of variances. Okay. All right. So remember, analysis of variances, you're basically comparing the means or the X bars of groups to one another. So you guys were paying attention during my sailfish talk. That's what I did with my ocean basins, to see if the average sizes in these different ocean basins were the same or they were different. So you can do one way or a two-way. I think two-way might be chapter 9 though. Okay, cool. So I'll review that myself tonight before I talk to you guys about it.
Jacob, do you happen to have the homework with you? Because I seem to not have my chapter.
Yes, I do have the homeworks with me. I can grab it now for you.
No choice. Only
I'm just like, some more.
I don't see it in my thing, so I'd be pretty sure I either handed back to you or it could be in a different little compartment. So I'll double check after, just to make sure. Yeah. So we'll double check after though. Okay, so this is a problem. Okay, so 8S1, we're comparing 3 groups. Group A, B, and C. I don't know what we're comparing, just that there's 3 observations in each group. All right, so A was, you had 2, 3, 4. B, you had 3, 4, 5. And C, you had 4, 5, 6. So the sample mean for each of these individually is 3, 4, 5. And then the overall mean, which is this 2-bar, is 4. Okay, so it's like mean. All right, and so the null is that the mean of group A is equal to the mean of group B, which is equal to the mean of group C. All right, and so we need to find our sums of squares total, among, within, and our degrees of freedom total, within, and among. And then we're going to find our F stat and our F critical value, and then we're going to compare those two, and then we're going to come with an outcome. All right, so that's the method of this. So we also have these two variables. That's an n, should be an n. And O is the number of observations in each group. And NT is the number of groups. Okay, so they're both equal to 3. All right, that's just I don't really know why I wrote that, but moving forward. So the sums of square total is equal to your individual observation of each group minus the overall mean. So yeah, so I actually write this, move this over here. I'm gonna kind of follow the same like matrix, this 3 by 3 here. So it would be 2 minus 3, or sorry, 2 minus 4. Together, squared plus 3 minus 4 squared plus 4 minus 4 squared, yada yada yada. Okay, so from here on out, I'm just gonna write what this equals. Follow that part. 1 squared plus 0 squared. Plus 1 squared.
That's fine. We did it.
Okay, so 2 minus 4 is 2 squared. 3 minus 4 is 1 squared, and then 4 minus 4 is 0 squared. All right, so when you do all that fun stuff and you add them together, you get 12. Okay. And so the degrees of freedom total are your n sub 0 times your nt. That's why I wrote that. Minus 1. Okay. So 3 times 3 is 9, minus 1 is 8. And then so now we're gonna do the within. So I'm just gonna write this over here. SST equals to 12.
Wait, so NO is, how come it's not 9? Because there's no total observations.
Because NO is just the number of observations per group. Sorry,
Okay, thank you.
forgot to write that. Yeah, good call. SSN and TF T TFW TFA.
Is the -1 for DST just part of the formula?
Yes. And then where is this with 8? Okay. Let me just double check this what that is. Yeah, it's NT times NO minus 1. Okay, and then the sums of squares among is the mean of the group minus the mean of the total. Okay, so again, I'm going to be following this matrix. So I'm going to go this way, boom, boom. Okay, so it would be 3 minus 4 squared plus, I just, no. Okay, 2. Sorry about that, everyone. 2 minus 4 squared, and then wait, am I doing the right one?
Of the group minus the like total mean.
Yes.
So it would be 3 minus 4.
3 minus 4.
What happens? Second guess myself. 3 minus 4. Yeah, because I literally just looked at my paper and I was like, wait a second. That doesn't equal 1. Okay. And then 4 minus 4, 2 plus 5 minus 4 squared. And then you basically have these 3 columns, or these 3 rows 2 more times. So that would just be 1 squared plus 0 squared plus 1 squared. 1 squared. All right. And then, so again, this would just be 1 squared. This would be 4 squared, 0 squared. And this would be 1 squared. Okay, so then you get 1, 2, 3, 4, 5, 6. So your sums of square among is at 6. And then your degrees of freedom among is NT minus 1. Okay. Well, good on that one. So this would be 2. And then lastly, we're going to do the sums of squares within. And that is the individual observation in the group minus the group mean squared. So, yeah. So this would be 2 minus 3 squared plus 3 minus 4 squared plus 4 minus 5 squared. Yeah. And then plus this whole row is 0. Okay, so just whatever. And then this one is 4 minus 3 squared plus 4 minus 4 plus 5 minus 4. All right, so again, we get a value of 6 because 1 plus 1 is 3, plus 1 is 0, is 4, 5, 6. All right, so that sum of squares within is 6. And then our DFW is NT times N naught minus 1. So we have 3 times 2 equal to 6. So our DFW is 6. All right, so those are our 6 variables.
Or DFW, sorry.
Like this.
Yeah.
Okay. No, I'm gonna leave that up. All right, so now we have all of those values. And so to find our F statistic, you do sums of square among divided by degrees of freedom among over sums of square within divide degrees of freedom within. So you get 6 divided by 2 over 6 divided by 6. That gives you a value of 3. And then our F critical value is degrees of freedom among equals 2, degrees of freedom within equals 6, and an alpha of 0.05. And you get a value of 5.14.
This is in what table?
Find that out.
F
It's the F critical, right? Yeah. The table on page 505. So you have your A value is 2, and then your W value is 6. Or do you do it the other way around? 2 and 6. Yeah. So V1 in this top corner here is telling you like that's your first degrees of freedom, the alpha, or degrees of freedom among. And then the V2 is your degrees of freedom within. So you do 2 over on the top row and then 6 down, and you get 5.14. All right. And then so we get 5.14. And so our F stat, the way he's doing the test is if you feel comfortable doing it in Python, do it in Python. If you feel comfortable doing it by hand, do it by hand. There's no, from what I understand, there's no, you have to do this by hand or you have to do this by Python. So it's like,
There will be problems that like you need Python for it.
you can do all these Python pretty much.
Okay,
So like,
but you can do all of them by hand.
you can also do them all by hand.
Okay. Do you know if it's gonna take me off with the graph and calculator?
Oh, yeah.
Okay.
Yeah, that's fine. He just doesn't want you using the calculator on your phone. So like, we know it's open book and open note and open whatever, but like as soon as you start looking stuff up on your phone, that's when like he's gonna, cut it off. Anyways, your F stat is less than your F critical value, which leads you to fail to reject. So I'll write this over here. F stat is less than F crit. Fail to reject. F stat is greater than F crit. Reject. Okay. And so we're saying that the underlying means are true. So that mu A does equal mu B equals mu C. So if you did this in Python, you get a p-value of 0.125, which would also lead you to fail to reject. All right. So that's how you do that one by hand. It takes a little bit of time, but you guys can do it. So then, what time is it? Oh man, we got 20 minutes to do one problem. Like on this homework, I think the only ones that you required to do by hand were S1 and this Kruskal-Wallis test. The rest of the answers he gave me were just on Python. Oh yeah, the ANOVAs on any sort of software is like the simplest thing to do. Like in R, the software I ran, like all you have to write is like AOV. That's it. That's all you have to do. So the Kruskal-Wallis test is a comparison. It's a non-parametric way alternative to doing ANOVA. So instead of comparing the means, you're going to be comparing the medians. And so basically, the only difference I shouldn't say basically the only difference, but like instead of your null being means, it would be medians. All right, so this one is, I think it's like 2 drugs or something.
What number is it?
813. Damn, I'm hungry. Thank you. Oh, this is this. Oh wait, that's not that question. Okay, that carb question was annoying. Which one was it? 213. Okay. So you have what is this talking about? Tobacco plants assigned 3 groups of 5 plants each. 1 group was untreated, 1 was infected with TMV, and 1 was affected with TRSV. After 1 week, yada yada yada. Does the infection by either virus affect the activity of the enzyme? And in this question on the book, it says use the Bonferroni home test. And in his thing, he said don't use that test. So we're gonna be using the Kruskal-Wallis test. He said use the Kruskal-Wallis test. So yeah. So first, I'm just gonna write out the values of this table here. So you have your control group. Then you have 1.47, 1.62, 1.06, 0.89, 1.67. I'm on 813. We're doing a Kruskal-Wallis test. TMV is one of the things that something 2.44, 2.31, 1.98, 2.76, and 2.39. And then TRSV was the other something, and it's 2.87, 3.05, 2.36, 3.21, and 3. No. So what we need to do is then rank them all together. And so again, since I already have the ranks here, I'm just gonna write them next to each other. Okay, so okay, and then you sum up these. So that's 15. That is the 13 that I wrote. This is 43, and this is 62. Okay. And so add those all together. 15, 43, 62 equals 120. Okay. And then the H-stat, I want to give you guys the formula for H-stat if you wrote it down. Oh, we didn't. Okay. So, do you write down the formula for H-stat?
Do you think we'll make us use this test if we don't have to?
What do you mean?
Like you could just use it, like you could just do this the other way and get this answer, like with an F and stuff.
Yeah, but this is the non-parametric version of it. So this is if you weren't assuming normality. Okay, so I'm not sure if this is just happenstance, but the one he gave in the book and this one here have the same start to their H-stat formula, which is H-stat equals 12 over 15 times 16 times 1 over 5. And I have no clue where those numbers would come from. So that's why it's leading me to believe that that is a constant. Because like I said, that start there and the start that he has on the example and the notes are the exact same. But anyway, So then that is then multiplied by these sums all squared up together. And then subtracted by 15 plus 1, 3 times 15 plus 1. Again, starting to wonder where that number comes from.
It's 12 over NT times NT minus 1 times 1 over NO times the rank sum squared.
Oh shoot,
minus
what is it?
3.
All right, sorry. So
So it's the 12 over the N total times N total minus 1. And then that's multiplied by 1 over NO. Number of observations. And then that's the rank times the rank sum of one of them squared, and then the rank sum of the other one squared.
Yeah.
And then that's minus 3 times the total N plus 1.
I was like, there's no way there's like,
It was on his equation.
okay. Oh, that's right. He was saying this is the one where you gotta like use that equation sheet. Okay, cool. All right, sweet. So that's where that comes from.
Wait, you're gonna get the 15 and the 16 and the 12.
That's all from the the formula that's on the formula sheet. It's 12 for sure
Okay,
over NT times NT minus 1.
NT minus 1.
And then, so NT is your total number of observations. So since we have 5 observations with 3 groups, it's 15.
Yeah, I thought it was NT plus 1.
That's this side.
Because the other side.
Oh,
Oh, wait.
wait,
Is it
wait,
this side too?
15?
No, that one's minus 1.
Well, then why is it 15 times 16? Since 15 total
15.
observations. 16.
No, that's a good observation. Sure.
I have n times n plus 1 for mine. I don't know if that's right.
All right, maybe it's n plus 1 both sides.
Like it's NT and
That's
then
what I
NT
have on
plus
mine,
1.
But I don't know.
Yeah.
Yeah, it's just
It would make more sense if they're both 16 then. Because I'm just basing it strictly on what you have written down, so he has 16 on both these sides. So anyway, so 3 times 16 then. The sum, when you add or when you work this out, you get a value of, so 1 over 100 times is 5,918 minus 48. And that gives you a value of 11.18. Which your age statistic.
Where does the 1/5 come from?
1 over number of observations in each group and sub O.
Wait, sorry, please. Where's
T, total. So N sub O is it's part of this. I know I wrote this formula kind of way over here. But it's 12 over NT times NT plus 1 times 1 over N sub O. And then the sums of those ranks squared. So rank 1 squared plus rank 2 squared plus rank 3 squared.
the number of observations in each group?
Yeah.
Okay, 1 over 5. Okay, makes sense.
All right, so then our HSAT is 11.818. And then since we're looking at medians, we're going to be comparing it to the chi-squared critical value. So the chi-squared critical value, degrees of freedom is 2. Your alpha is 0.05. And the degrees of freedom are the number of groups minus 1. Okay, anyway, number of groups minus 1 is degrees of freedom. And then, so that's 2. So then when you look at this in the chi table, you get 5.991. Okay. And then since our H stat is greater than our chi critical value, we're going to reject the null. And so we would say the medians are not all equal. Thank you. I was like, there's no way that this would just like happen to be the same thing. I was gonna fail. All right, so that is 813 crustal walls, non-parametric way to do an ANOVA. Okay,
5.
so hopefully this will stay here tomorrow. Oh, I guess I could write another one.
Oh, yeah,
So when H stat is greater than chi squared critical, you reject and then when H stat is less than chi squared critical, you fail to reject.
You're good, sorry.
Okay, so that was, yeah, that was 5 through 8, kind of skipping 7, kind of skipping around 8.
And so that was, you, the distribution is not like normal.
So you would just say, like, this is just comparing the medians to the groups. So you would just say that these group medians are not. That's all you're doing.
Yeah, but like, why does he just text over like the,
Specifically, why we used it in this one was because he specified.
yeah.
It's just another, it would say like non-parametric normality data.
So this was assuming none.
Yeah, so this is just doing the ANOVA, but with. Alright. Just realized like that whole last question, this wasn't aimed right at it, so. I'm just gonna let it sit here for a second. Get a recording of stuff.
Thank you.
All right, you're welcome. Yep.
Thank you. See you
All
tomorrow.
right, yep, I'll be here tomorrow, same time, same place. No worries, have a good one.
Do we use these forms at all?
I don't think we're gonna need Z-scores on this,
How
test.
likely do you think we'll put like the stuff from the last?
I don't think he's gonna give you like any specific question from the last. You're welcome. But I mean, you guys will have all your homework and stuff. And bring your midterms too.
I'm bringing every single.
Yeah, bring everything.
Literally, like, I'm gonna take one of those whole tables and just run everything.
I'm
That's a
gonna,
little excessive.
I'm going to the printer, and I'm gonna have to print out like 50 pages.
Just run the whole course.
God damn.
I don't know.
I'm
They're sitting right there, but they just lost their Arches National Park. Well, I appreciate